Alrighty, so this is the solution to the 2011 scholarship question on page 12. It is question 3A. So this is a titration calculation question, and we are starting with a mixture of oxalic acid and sodium oxalate and carrying out two titrations to figure out how much of the mixture is oxalic acid, how much is sodium oxalate, and how much is impurity. So we have been given two tests. So we're going to start off with test 1. And if we look at test 1, we are titrating against permanganate. So this is a redox titration. And the key point here is that the permanganate will get reduced to Mn2+, and it will react with any oxalate ions present, which will get oxidized to CO2. So we're going to start with working out the number of moles of the MnO4-, and that's going to be C times V, and the concentration of the MnO4- is 0.01803. And the volume is average volume is 23.35. So we divide that by 1,000 to get 0.02335, and that is going to give us 4.210 times 10 to the minus 4 moles of permanganate. And as we all know, in the second step of a redox titration, what we need to do is we need to use our mole ratio. So in this case, our mole ratio is MnO4- to oxalate. And if we balance our half equations using redox, we will come to the realization that we need 2 moles of MnO4- to every 5 moles of C2O4-. So we take our 4.210 times 10 to the minus 4 moles of MnO4-, multiply that by 5 over 2, and that will give us 1.0525 times 10 to the minus 3 moles of C2O4-. Looking back at the question, that is in 5 mils. What we want to do at this stage is go back to the original. So our original sample was in 100 mils. So therefore, if we multiply by 20, that gives us 0.02105 moles of C2O4 in 100 mils. So that's our first answer, right, 0.02105. Okay, so now we're going to look at test 2. Okay, and test 2, if we're looking back at the question. Okay, so this is test 2. What we're doing in test 2 is we're taking 10 mils of our mixture and we are titrating that against sodium hydroxide. So this is an acid-base titration. Okay, so let's start with what we've got in the question. We can calculate the number of moles of NaOH, right? And that is going to be, the concentration is 0.1040, and the volume average titer is 17.30 mils, so 0.01730, and that is going to give us 1.7992 times 10 to the minus 3 moles of NaOH. So then we need a mole ratio. Next step is a mole ratio. So NaOH plus H2C2O4. This is a diprotic acid. So just think of this as being like H2SO4. So if you substitute the C2O4 for SO4, then you will get Na2C2O4 plus 2H2O, and you will need 2 moles of sodium hydroxide to balance that. So the mole ratio that we need is 2 moles of NaOH to every 1 mole of oxalic acid. So we take our number of moles of NaOH, which we previously determined to be 1.7992 times 10 to the minus 3, and we divide that by 2 to give us 8.996 times 10 to the minus 4. That's moles of H2C2O4, and this time 10 mils. So we're going to multiply that by 10, and that gives us 8.996 times 10 to the minus 3 moles of H2C2O4 in 100 mils. Oops, let's just make sure you can see that. Okay, so now we are at the point where we have got the number of moles, but we've just got a little bit of jiggery-pokery thinking to do here. So we know that our acid-base titration, which is titration 2, actually gives us our actual number of moles of H2C2O4, and that is our 8.996 times 10 to the minus 3 moles. However, our first test that we did, which was our redox titration, was where we reacted our mixture with our permanganate. Now, permanganate will oxidize both the C2O4 minus ions from that and the C2O4 minus ions from that. So this number here, which was 0.02105, is the number of moles of both of those together. Okay, so we've got this number, which gives us both of these moles, and we've got this number that gives us the acid only. So we need to do a subtraction, and this is a common thing that we have to do in scholarship type equations where we tend to have lots of mixtures. So if we go 0.02105 subtract 8.996 times 10 to the minus 3, we get 0.012054 moles, and that is of the Na2C2O4. Well, the C2O4 from the Na2C2O4. Okay, so now we have in 100 mils, we know in 100 mils, we know that we have 0.012054 moles of Na2C2O4 and 8.996 times 10 to the minus 3 moles of H2C2O4. So those are our moles in 100 mils. So what we're going to do now, sorry about that, what we're going to do now is we're going to go back to the question and we're going to figure out, we're going to figure out that the question is asking us the mass fractions of those two. Oh, I'm sorry about this. Okay, so to get the mass fractions, we need to use the molar masses, which are thankfully given to us. So we need to multiply this one by the molar mass of the NO2, which is 134 grams per mole. And we need to multiply that one by the molar mass of that one, which is 90 grams per mole. And that is going to give us the following numbers. So the Na2C2O4 is going to be is going to be 1.615 grams. And the H2C2O4 gives us 0.8099 grams. And they want a mass fraction. So for the Na2C2O4, we're going to go 1.615 grams over the total, which is 2.496, which was our mixture. and that gives us 0.647, which is our mass fraction. And then for the H2C2O4, we've got 0.8099 grams over 2.496 grams, and that mass fraction is 0.324. And our last one is the difference. So if we add the 1.615 to the 0.8099, we get, and we subtract that from the total, we get the difference, which is 0.0711, which is our impurity, over 2.496 grams, and that is 0.0285, which is our mass fraction of the impurity. So those are our three answers. Boom.